Today we are going to be talking about dispersion. We're going to focus on what dispersion is and how it occurs, the individual components that make that up, but we're ultimately going to be able to talk today about why the effects of dispersion cause rainbows. And so in order to understand that, we first have to understand what dispersion is. And dispersion is defined by breaking up the individual components of a wave. So you have a wave such as white light, and because of Snell's law, as it passes from one medium to another, this white light is broken up into its individual components. And we'll talk a little bit more about what Snell's law is in a moment for those of you that are unfamiliar with this. But basically what happens is white light passes into this prism. It's going to break up into its individual wave components, and we start to see different colors coming out. So white light, since it's composed of the different colors of the visible light spectrum, we start to see a rainbow appear. And so this is what dispersion ultimately is just this breaking up of these individual components of a larger wave. And so in order to talk about why this occurs, it's important for us to understand the law, or Snell's law, which is the law of refraction. And so in order to talk about this, we're going to talk, I want to give you an example of what Snell's law looks like. So we're going to have, for this example, have some water here, which will be our secondary medium that we'll talk about. Just kind of fill it in there a little bit. And then we're going to have our sunlight, or just any incident light, traveling here that's going to hit this light at this angle. And as it does so, it's actually going to change direction. It may not be this dramatic depending on the medium, but I want to do that just to kind of show this relationship a little bit more. And we learn that the index of refraction of one medium, so we'll call that N1 for this, and that'll be, the N1 is going to be our refractive index of air. And we'll talk a little bit later about what that refractive index is and how we can derive that, because it's very important for us to understand that for dispersion. Is going to be equal, to the sine of theta 1. So that's the angle between the normal and the ray of light. So we'll put that in here, sine of theta 1. So the refractive index of 1 times sine of theta 1 is equal to the refractive index of 2, and I'll label that in a second, times the sine of theta 2. So theta 2 is here, and this is the refractive index of 2 will be the refractive index of our water. And so what's happening here basically is that this index of, or this ray of light is coming in. As it hits the surface of the water, the velocity of the light is going to slow down. And because of that slowing, it's going to change the angle at which that the direction at which that light is traveling. And that's really important because that gives us our equation for our refractive index, which is really important to understand with dispersion. So this refractive index is going to be equal to the speed of light divided by the velocity of the ray of light in a specific medium. So since the speed of light, this is the speed of light in a vacuum, this C right here, and since the speed of light in a vacuum is very close to the speed of light in air, our refractive index of air is actually close to 1, whereas the refractive index of water, the light is going to be slowed down, which is what causes this change in direction of the light. And it's closer, the refractive index is about 1.33. And that's important because that will ultimately show you in this equation up here that this theta is going to change as light moves from one medium to the other. And the reason this is so important for dispersion is because, going back over to our prism example, I'm going to redraw this a little bit, make it a little bit bigger, a little bit easier to see. So we've got white light with its individual components that are moving. We can see that each of the individual refractive indexes for each of the different colors is actually different, because this refractive index over here, n, is going to be proportional to the wavelength of the light. And since each of the different individual wavelengths of the different colors are different, the refractive index is going to change. And so because of this, with red on the visible light spectrum, its wavelength is a bit, the wavelength of this red light is going to be larger than the wavelength of, say, blue light. And because of this, we start to see this separation of the light as it's moving through. So since the wavelength is larger or smaller for blue, the refractive index, this refractive index it's inversely proportional to the wavelength, because it's directly proportional to the velocity. And since the wavelength of blue light is smaller, the velocity is going to be smaller, causing the index of refraction to be larger, causing a greater theta change or angle change in blue light compared to red light. And since this is occurring, we're going to start to see that as it hits this other end of the prism and is refracted again, that these colors start coming out in different spots, and they are separated from one another. So I'm going to kind of fill in the rest of the rainbow here the best I can with the colors that I have, so you can kind of see how this is occurring. So there you've got the different rainbow or colors of light coming through and as a rainbow. And so the reason that this is so important to understand when we're looking at rainbows is because with rainbows we have refraction occurring as light passes through a raindrop. So I'm going to draw a raindrop here. And as the raindrop's sitting here, we have sunlight coming in. And it hits this raindrop. And as it does so, the dispersion occurs, and these different wavelengths of light are separated from each other. And then also important to note in kind of the creation of a rainbow is not only is it refracted through this raindrop, but also it's going to be reflected off of the back of the raindrop. And so that's why you're always only going to be able to see a rainbow as you are facing away from the sun, because this reflection occurs. And it's also important to know that the law of reflection states that the angle of incidence equals the angle of reflection, which means that this light is going to come out in this direction. And then I'm going to use green here instead of blue since our raindrop is already blue. That's going to be refracted more than red light, and then it's going to reflect off the back here. We'll draw, sorry about that. I'll draw kind of our normal here so we can see how this is, sorry, that was really bad. I'm going to see how this reflects off. But ultimately we're going to see that this is going to reflect off at a more shallow angle than that of red light. And so we see that green light is going to come out above red light. And the reason that this is important, or the reason that we kind of see this phenomena is important for us on the ground, because this gives us kind of the order for which we see the rainbow. So I'm going to draw us the observer down here. I'm kind of happy because we get to see a rainbow today. And we're going to see that as this red light continues to travel, it's not going to be a perfectly straight line, unfortunately. But we're going to see that this hits the eye of the observer, which is going to cause that we see red light kind of up here. And I'm going to kind of draw the separation of this a bit dramatically. It's not this dramatic in real life, but I want us to be able to kind of visualize this. And so the reason also that we will see green light or blue light a little bit further down is because of how the reflection and refraction occur for green light, or for these lights or colors that have a lower frequency come off at a more shallow angle. We only see this because of how all of this occurs. Sorry, let me draw this out really quickly. Sunlight coming in here, green's going to come down, and red will come out like that. So if I filled in all of this, you would see that these different colors of the rainbow would start to appear. I'm going to fill in everything that would be yellow and orange with just yellow, since I don't have a orange marker, unfortunately. And then I will show our blue down here. If I continue to fill this in, we would see all of these individual components. And it's the reason that we have all of this kind of separated as such that we start to see a rainbow form with the red at the top and blue at the bottom. Sorry, this rainbow is going to be kind of sad, but just bear with me. Oh wow, I'm not going to have enough room for green. But ultimately, this is where these structures of the rainbow comes from, is through this diffraction pattern of light in the air after a rainstorm. Also important about diffraction is it allows us to, in science, to be able to observe like the structures of proteins. Dispersion, sorry. Dispersion allows us to kind of see the different protein structures. We can use dispersion for that to kind of break up wavelengths and to understand them better. And it's also important to kind of understand dispersion because it's important in fiber optics as well. A lot of light can be dispersed, and so that's an important thing to be aware of. But I hope you enjoyed this video today and were able to learn a little bit more about why dispersion matters and why dispersion allows us to see rainbows after a rainstorm. Thanks for tuning in. Bye.